This is going to be a pretty chock-full screencast that I have for you tonight. There are three things that we're covering, and they're fairly disparate, frankly. I'm not sure how I decided that these would be three things that I'd try to cram into one screencast, but oh well, here it goes anyway. So the first concept is the exceptions to the octet rule. And I'm not going to go into huge amounts of details as to why these exceptions exist, because frankly it's way beyond the scope of what we're doing, and in some cases I don't even get it. No matter how many times I try to go back and figure out what's going on, it doesn't make a whole lot of sense. So clearly you don't need to know how exactly these things work. But there are three fundamental times where there are going to be exceptions to the octet rule. The first of which is when there are odd numbers of valence electrons. And this is going to lead to a very specific event. So let's take a look at this one, and we're going to use as an example of this something called a free radical. You guys have probably heard of free radicals before, and they are incredibly reactive species that will connect to a lot of things, especially to halogens in particular. Because halogens love to have electrons, and you'll see in a moment that these free radicals have a single electron, an unpaired electron, cruising around waiting to be bonded with something. So a good example of that is something called nitrogen monoxide. And with nitrogen monoxide, if we were to look at the Lewis dot structures for nitrogen, you know that there are that's right. There are 5 electrons around nitrogen. And then with oxygen, we have 6 electrons around it. So we have 11 electrons altogether. Now, when there are an odd number, obviously you're going to have a hard time having an even number octet being formed here. And so that's why we have issues here with these odd numbers of valence electrons. And what happens here, oddly enough, is that you have something that looks like this, and notice we have an electron that doesn't have a pal with it, right up here. So all these are unshared pairs. We have a couple of shared pairs here, and an unshared pair, and then we have this one all by itself. And obviously you can see that oxygen is all set. It's got 8 electrons associated in its valence. It has to share a couple from nitrogen, but it's got 8, right? We have the 4 here plus the 4 unshared pairs. Nitrogen's a little weird, right? It has the 4, 6, 7 around it. So clearly it's not following the octet rule, and yet it's totally fine existing as it is. However, when I say it's totally fine existing as it is, as I said earlier, highly reactive, because that single electron, the one that I just circled right there, will want to connect with something that needs an electron. So any of the halides that are looking to fill their octet would love to bond with this nitrogen monoxide. Okay, so there's the first exception. Let's see, I guess I need a new page. The second situation we have where there are going to be exceptions is when there are too few valence electrons. And in fact, you know one really well, which is hydrogen. You know, hydrogen doesn't need to have 8 to be satisfied. And if you just take something like hydrogen gas, or H2, it looks like that. And clearly that means there are only going to be 2 electrons in hydrogen. Now, you also probably understand that that makes a lot of sense, because hydrogen only has the 1s orbital, which can only hold 2 electrons anyway. So no surprise here that it's going to be totally satisfied only with having the 2 electrons. But there are other cases that go beyond the simple hydrogen example. For example, whoops, didn't need to put an H there. Let me erase that for a moment. If we take something like boron trifluoride, BF3, which is, I think, something that you guys made today in class. And when you take a look at boron trifluoride, we have a situation that would look like this. Fluorine has the octet filled, right? Each of the 3 fluorines have 8 around them. But the boron only has 6 electrons as a result of the covalent bonds that it has there. And that seems rather odd, right? Well, of course, it is rather odd, but know that boron is completely comfortable, and experimental analysis has suggested that it doesn't try to form a double bond with any of the fluorines or anything like that. It's perfectly happy having 6 electrons in its valence shell. Oh, and by the way, this is a trigonal planar. And hydrogen here is linear. Okay, good review of those things. All right, and then the last situation is when you have too many valence. Oops, I didn't mean to. Give me my eraser. Too many valence electrons. Okay, and in this case, oh darn it, I'm running out of room here. There we go. Let's take something like phosphorus tetrachloride, pentachloride. And with this thing, keep in mind that when you are dealing with an atom in the 3 principal quantum level, the 3rd principal quantum level, so this is period 3, you are also going to introduce the 3D orbital. Now, that doesn't mean you necessarily have electrons to fill the 3D orbital, but it exists as an open space for you to put electrons. And that's going to be a really important thing to consider here. Again, let's say I just map this out. Here's the 3s orbital. Here's the 3p orbital with slots for 6 electrons. And then here's my 3d orbital with slots for 10 additional electrons. So at the 3rd principal quantum number, we have a lot more room right here, right, to put in excess electrons if we need to, which is what allows the phosphorus to be able to do this. And if you look at phosphorus on the periodic table, you'll see it's in the 3rd period. So let me scooch up here, give it some space here. And if I put P as my central atom, I would then have Cl over here, Cl over here, Cl over here, one down here, and one up here. And these would all have their 8 plus the shared, so the 6 plus the shared here, all the way around here. And in fact, this species, this molecule, has kind of it's a cool thing because this is a new shape that you guys haven't seen, although it is kind of a combination of 2 things that you have seen. This is called trigonal bipyramidal. Bipyramidal, 2 pyramids. And you can actually maybe see that, although what's better for me to do is probably insert a picture. Let's see if I can put it here. Yeah, here we go. Perfect. So check this out. This is a model showing the trigonal bipyramidal going on here. And just so you know what's going on here, here's a chlorine, another chlorine, and in the middle we have our phosphorus there. And you can also probably see, because of the shape here, here's one of the pyramids, right? And then you have the one right underneath it that would exist. I can't really draw the alignment back there, but you can see how we have 2 trigonal pyramidals, basically their bottoms stuck together in this form. In some ways I've made it more of a mess by putting in these things, so let me just erase that stuff. I'll even erase the chlorine and phosphate so you can more easily see what's going on here. Okay? Kind of cool, huh? Alright, so there we have... actually, let me do one more exception, because there's one nutty one that I think is pretty cool, and that is sulfur hexafluoride, or SF6. And sulfur hexafluoride has sulfur as the central atom with fluorines all around it. Notice that halogens love to be involved in this because halogens so crave electrons and bring a ton of electrons to the party too. This actually forms an octahedral. shape. Sort of think of that as kind of like a pyramid, two pyramids that are stacked like the pyramids in Egypt. Their bases glued to each other. And again, this is all due to having d-block availability of orbitals, so you can put all these extra, oops, didn't need to put that guy in there. You can put all these extra electrons in there without having any issue. Simply having the space to do this. Alright, cool, huh? Love it. I wonder if I have a picture of, I won't bother. You guys can probably understand what that shape looks like. Okay, so let's move to the next concept, and that is of resonance. And for resonance, I'm going to take a thing that's a kind of a molecule. It's an ion that you guys have seen, a polyatomic ion, in fact, carbonate, right? This is the carbonate ion. Now, even though it's an ion, you can still, as you well know from the last test that you guys took, you can still make Lewis dot structures showing ions. And if you did so, you would see that you could make a Lewis dot structure that would look something like this for carbonate. Oops, that's a no. All right, and that satisfies the octet for both carbon and all three of the oxygens that surround there. This is charged, so I can't be naughty and leave off that piece right there. But what's cool about this is, in fact, this isn't the only thing that I could draw to make it look like this was the proper Lewis dot structure. So let me just copy this and paste it over here. And in fact, what if I decided, instead of having the double bond right here, if I moved it to over here? Well, I could do that. Of course, I have to rearrange a couple things here and there, so I have to add that. I have to erase a couple of my electrons over here. Oops, sorry about that oxygen. And then I'd have to erase also the double bond here, make it a single bond. But if I have a single bond there, then I do need to add in a couple of more of my lone pairs or unshared pairs of electrons. So notice they're very similar to one another. It's just like they're mirror images. And yet there's even a third one, if I were to put this in here, I'm just pasting this in, where I could have the double bond in, I guess you would call it the top situation here. So I put the double bond here, I erase the extra double bond, just make this a single bond over here. If it is a single bond, of course I need to add a couple more electrons around there, and then I do need to erase one of these three pairs of electrons, since we have the double bond action going right in here. So I'll go ahead and zap those guys right there. So you can see that I have three different structures, right? And each of these structures are accurate representations of carbonate. However, what's absolutely nuts here is that none of these actually exist. When you do experimental analysis of carbonate, you find out that all three bonds are actually identical to one another. So it's not like you'd see that there'd be a single bond, and then you'd have a double bond somewhere. In fact, you have something between a single bond and a double bond that exists when you do the reality check of this molecule or of this ion. And so it's sort of like a 1 1/3 bond that exists here. Now, we refer to this as resonance, and resonance is a way to describe that there are multiple different ways in which you can draw the Lewis dot structure, and they'd all three be right. But again, in some ways, all three of them would be wrong at the same time in terms of the reality of what exists out there. Shoot, you know what? I've already gone to 15 minutes. I'm just going to talk to you guys tomorrow more about polarity as we're building up those molecules in class. And hopefully you'll have a chance then to ask me questions about it too, live and in person. Okay, so I'll stop right here, and I'll see you folks tomorrow in the afternoon. Bye.